Hello friends, here's a question worth asking. In a world full of new databases, AI-native data stores and graph engines, why is understanding database schema and relational operators more relevant than ever? Look at this number. According to the 2025 Stack Overflow Developer Survey, 55.6% of developers use PostgreSQL. That is up from 48.7% just 1 year earlier, the largest single-year jump in its history. And just this month, on June 4, 2026, the PostgreSQL Global Development Group released Postgres 19 Beta 1, a landmark release built directly on top of the schema and relational model we are about to learn. In this video, we will go from the very definition of a database schema, through the 6 core relational operators, all the way to real SQL running inside Postgres 19 today. Let's start with the blueprint. Alright, so what exactly is a schema? Think of it as the blueprint of your database. Before a single row of data is stored, the schema defines what the data looks like, which tables exist, what columns each table has, what data type each column holds, and what rules or constraints apply. Take a simple e-commerce example we will use throughout this video. We have a customers table with columns for ID, name, and email. We have an orders table with ID, customer_ID, amount, and status. The customer_ID column is a foreign key, linking each order back to a customer. That relationship is part of the schema. The key distinction to lock in is this. The schema is a logical design, the abstract structure of your data. Physical storage, how that structure actually lives on disk as files and pages, is a separate concern entirely. The schema is the contract every query must respect. Now let's meet the 6 core relational operators. These come from relational algebra, the mathematical foundation that every SQL engine, including PostgreSQL, is built on. First, select, written with a sigma symbol, filters rows. Give it a condition, and it returns only the rows that satisfy it. Second, project, written with pi, trims columns. You pick exactly the columns you want. Third, union combines 2 compatible tables, returning all rows from both. Fourth, difference returns rows that appear in the first table but not in the second. Fifth, Cartesian product pairs every row in one table with every row in the other, producing every possible combination. And sixth, rename, written with row, gives a table or a column a new name, which is handy when building complex expressions. These 6 form a complete set. Every other operation you will ever use, including joins, is derived from combinations of these 6. Speaking of joins, that is exactly where we are headed next. Here is the interesting part. Join is not one of the 6 primitives. It is derived from Cartesian product followed by select, but it is so useful that it gets its own name and its own SQL keyword. The idea is simple. Given 2 tables that share a related attribute, join finds the rows that match and merges them into one combined row. In our example, customers has ID, name, and email, and orders has customer_ID. An inner join on that shared key returns one row for every customer order pair that actually matches. Alice placed 2 orders, so she appears twice. Bob placed 1. Carol has no orders, so she does not appear at all in an inner join. A left outer join changes that. Carol appears, with null filling the order columns. A natural join automatically matches on any column that shares a name in both tables. In SQL you will write all 3 daily. Inner joins are the default workhorse, outer joins preserve unmatched rows, and natural joins are a shortcut when column names align. Joins are where relational algebra meets real-world data combination. Let me show you how everything we have covered lands in actual PostgreSQL 19 code. First, create schema store creates a named namespace that organizes our tables. That is the blueprint from slide 2, declared in 1 line. Next, we write a select that applies 2 relational operators at once. The where clause is select, filtering for completed orders. The column list is project, keeping only name and amount. The inner join is the derived operator from slide 4, matching customers to orders on the shared key. That one query combines 3 operators from our core 6. Now here is the exciting part specific to PostgreSQL 19 Beta 1, released just this month. The new SQL/PGQ feature lets you declare a property graph over those exact same relational tables and query relationships with graph-style pattern matching. Underneath, PostgreSQL rewrites the graph pattern straight back into relational joins. Your schema stays relational. You just gained a new way to express traversals on top of it. Alright, let's bring it all together. A database schema is the blueprint, the precise definition of tables, columns, data types, and constraints that every query must respect. Relational algebra gives us 6 core operators to work with that blueprint. Select filters rows, project trims columns, union combines tables, difference finds rows unique to one table, Cartesian product pairs every row with every row, and rename gives things new names. Join is a derived operator built from those primitives, and it is the one you will write in SQL every single day. Every where clause, every column list, every join you write is one of these operators in disguise. And as PostgreSQL 19 Beta 1 shows us this month, even brand new capabilities, like SQL/PGQ graph queries, are ultimately rewritten back into relational operations by the database engine. The theory is not academic. It is alive inside every production database running right now. Go download Postgres 19 Beta and try it yourself. I will see you in the next video.